Hello student, today we will study the first practical. Uh, the practical aim is simulation of chopper fed DC drive. Okay, this is the schematic diagram of a chopper fed DC drive where a chopper is used to drive a DC motor. You can observe here the basic constituents of a electric drive. Okay, this is nothing but a source. This is a power modulator. This is a motor, and this motor can be coupled to a particular load. This is speed sensor, okay, sensing unit. This speed is sensed and given to a control unit. Okay, this is the part of control unit. Again, the control unit is given one more input. Okay, we can call it as input command. Input command. Okay, so we can relate this diagram with the basic diagram of electric drive. Okay, so first we will see how a chopper works, and then we will go for actual practical. So chopper is a DC to DC converter. Okay, there are basic three types of chopper depending on the what is the input voltage level and what is the output voltage level. Okay, first is the buck chopper, or it is also known as a step down chopper. Because the input voltage, input DC voltage, which is given to a chopper circuit, it steps it down. Means what? The output voltage is less than the input voltage. Okay, we can show here the less than the input voltage. Second type is the boost chopper, which is also known as step up chopper. Step up chopper or step up DC to DC converter. Okay, obviously here the input voltage is boosted. Okay, means what? The output voltage is greater than, sorry, output voltage is greater than input voltage. And third type is the buck boost converter. Buck boost converter, okay, where the voltage level can be stepped down or voltage level can be stepped up, okay, as per the requirement. So in this practical, we are using a buck chopper. We are using a buck chopper. The schematic diagram of this buck chopper is like there is a DC source which is given to a controlled switch, okay, which is also known as a chopper. Okay, I will write it as only a symbolic representation as CH. Okay, and this is given to the load. Again, it is given, there may be a smoothing inductance present there. In this case, the load is armature or DC motor. Okay, and there is diode is also there. Okay, this is the basic circuit diagram of buck chopper. Okay. Suppose this DC input voltage VDC is equal to 220 volt. Okay, and suppose this armature or this DC motors rated speed is 1500 rpm. Okay, means what? uh, this chopper, okay, this buck chopper can control the output voltage given to the armature of DC motor to change the speed from 0 to 1500 rpm. Okay, the voltage equation for buck chopper is V output or V naught is equal to delta into VDC. Okay, where the range of delta is from 0 to 1. Okay, when delta is equal to 0, okay, means what, the switch is always off, then in that case V naught is equal to 0 volt. And as delta increase to 1, V naught becomes equal to input voltage VDC. So it means the output voltage range, okay, range of output voltage is from 0 to VDC, that is input voltage. Okay, and in this case the VDC is equal to 220 volt. Okay, means what, by changing V naught from 0 to 220 volt, we can get speed from 0 to rated speed, that is 1500 rpm. Okay, means what, this is armature voltage controlled method. Okay, we know that the speed range for armature voltage method from 0 to rated speed or base speed. Okay, so we will see the same diagram is there or not. Okay, you can observe here. Okay, this is the common terminal, okay, which is shown as a ground. This is a common terminal. So you can observe here the DC voltage is here, the chopper is here, the diode is also at the same location, the inductor, smoothing inductor is there, and the load, that is armature. Okay, you can see here the field is provided with a independent voltage source, and the armature is connected to the output of the output of the this buck converter. Okay, the one terminal is connected here, the other terminal of armature is connected to ground. Okay, so we can say that this is a can be this drive can be related to the basic diagram of a chopper. Now we will see how it operates. One minute. I will erase this part. Okay. So for getting the idea of how this operate, we will see the signal flow here. Okay, wait for a minute. Okay, we have studied the closed loop speed control scheme. I will draw this closed loop speed control scheme here, and we can relate with this diagram. Okay, in closed loop speed control technique, the load, okay, in this case is the armature of DC machine. Its speed is sensed. Okay, speed is sensed. This is omega m. Okay, and this is given to a comparator. The comparator compares this actual speed with reference speed, and the error is given to a speed controller. Speed controller error delta omega m is given to speed controller. Okay, the speed controller's output is current reference. Okay, to ensure this current is under allowable limit, okay, we will use a current limiter, and the output of this current limiter is again given to a comparator. Okay, this comparator compares the actual current. Okay, I will show here. This is the one terminal of armature, this is the other terminal of armature. Suppose the current is taken from this armature using current sensor, and this actual current of armature is compared again the newly formed current reference. Okay, and this error, okay, whatever the current error between the currents delta IA is given to a current controller. A current controller, and the output of this current controller is a pulse. Okay, and this pulse is given to chopper. In this case it is given to chopper, so it drives the chopper such that the output voltage given to the armature will be controlled. Okay, so this scheme is similar to that. Okay, here also the actual speed is measured, it is compared against speed reference, the error given is to speed controller. The speed controller is embedded with current limiter. The output of speed controller is the current reference, it is compared against actual current, the error is given to the current controller. Okay, in this case the output of current controller is shown as alpha. Okay, alpha is duty ratio. Okay, you can show it as a pulse or a duty ratio. Okay, we know that the V naught is equal to, okay, somewhere in some books the symbol is used as delta, or in some books the symbol is used as alpha. Delta into V or VDC. Therefore, delta is equal to V naught by VDC. Okay, means what? By changing the value of delta duty ratio, we can change output voltage. Okay, obviously the duty ratio is converted into pulses, and those pulses are given to the controlled switches of chopper. Okay, in this way output voltage of chopper is controlled, and actual speed of the machine is controlled. But here you can observe here the speed controller block they have used. The output of speed controller block, it is given to the current controller, and it is a hysteresis current controller. Okay, you can observe here the symbol of hysteresis. Okay, or relay. Some in some books it is called the relay controller, and most of the time it is referred as a hysteresis current controller. How it operates, I will show, or how it generates pulses. Suppose the speed controller sets a current, okay, of this magnitude. Okay, this is suppose IA star, and suppose the current has now has value equal to this. Okay, the hysteresis current controller does what? It defines a band. Okay, this is a lower band and it is a upper band. Okay, and it always confines the actual current between these two bands. This is upper band, this is lower band. Okay, and the width, this width is known as hysteresis band. Okay, so suppose the current is now at this point. Okay, obviously we have to increase the current, okay, so that the machine will accelerate to get the desired speed. So suppose the now the switch is on, so current will increase, current will rise. Okay, when it reaches the upper band, okay, the current is greater than the reference current, the actual current is greater than our reference current. Means what? We have to switch off the that particular power turning switch. So when it is switch off, the current will reduce. Okay, again when current touches the lower band, the switch is again turned on and current will rise again. Okay, and this process repeats number of times. So the average value of this actual current IA, okay, is equal to the reference current IA star, because the actual current oscillates around the reference current. Okay, this is how hysteresis current controller operates. Now we can find out the pulses from this. I will show on this axis. Okay, when we want to increase the value of current, okay, means what? The switch must be turned on, means what? Pulse is provided to that switch. Okay, so pulse is present, and when we want, when the actual current is greater than the reference value of current, okay, means what? The switch has to be turned off. Okay, means what? Pulse has to be removed. Okay, so there is no pulse. Again, if the current reaches the lower band, the switch has to be turned on. Means what? The pulse is given to the switch of chopper. Okay, this similarly we can get other pulses. Okay. So this pulse pattern, okay, this pulse pattern is provided by the hysteresis current controller. Okay, and this pulse pattern is given to the switch of a chopper. Okay. So you can observe here the current control, hysteresis current controls output is G. Okay, G means what? Gate pulses. Okay, and those gate pulses are given to the gate of GTO. Here the switch they have used is the GTO, gate turn off thyristor. Okay, so now we will perform the experiment. I will show you how to open that particular experiment. First open the MATLAB, then click on help. Okay, help option is available under home. Okay, under home. So click on help, then click on examples. A new window will appear where you have to search for sim power system. Okay. When you started to type, okay, options will be appear. Okay, you have to select under category sim power systems. Click on that. Okay, so these results will be there. So again, click on examples. Okay, you will see there examples. Okay, under examples, you will get two options: Simscape, components, and specialized technology. Click on specialized technology. Okay, under that, first practical simulation of chopper fed DC drive. It comes under power electronic models. So click on power electronic models. Okay, under power electronics, number of practicals are there. Okay, out of which we have to go for chopper fed DC drive. Okay, continuous. Okay, you have to select chopper fed DC motor drive continuous. Click on that. Okay, when you click on that, okay, this page will appear. Okay, you can read the information below, the description of the circuit, how to perform this simulation. They have given the information. Okay, you can read those. So again, then open this example. Click on open this example. When you click on open this example, okay, the particular simulation will open up. Okay, so this is a simulation. Okay, so what are the observation we have to take? I will show you the first table. Okay, this is the first table where we have to check the effect of moment of inertia on the acceleration of drive. Okay, so these are the parameters they have given. You have to put those parameters and just change the moment of inertia of the drive. Okay, they have told about put current limit of speed controller equal to 30 ampere. First we have to set current limiter of speed control. Obviously current limiter is come under speed controller. Double click on speed controller. You can see three options. One is the proportional gain, second is the integral gain, third is the current limit. Okay, put current limit equal to 30. Okay, it is already 30 ampere. Then set speed reference equal to 120 radian per second. Okay, the input command omega ref reference speed, okay, it can be a constant. Okay, or when you click on this switch, okay, it can change its position. Means what? A variable speed can be given. Step change in the speed can be given. Step change means what? For a small time it is running with 120 radian per second. After some time you can change the speed to 150 radian per second. Okay, means what? Instantaneous change in speed after some time. Okay, in this case we have to select the constant value 120 radian per second. Then hysteresis band of current controller has to be selected equal to 2 ampere. Okay, the option is again in the hysteresis current control, that is current controller. Okay, we have to set it equal to 2. It is already equal to 2. Again the speed is also equal to 120 radian per second. Last is load torque on the motor 5 Newton per meter. Here also we can either put load constant or we can give step change in load. In this case we have to give constant value. Okay, we have to put torque equal to 5 Newton per meter. Okay, so all the options are there. Just we have to put the what is the value of inertia. Okay, uh, change inertia of the in difference of 0.05. Okay, first take value equal to 0.05, then 0.1 to last reading you can take up to 0.4, 0.15, 0.2, 0.25. Okay, like that up to 0.4. So for 0.05, where we can place the inertia, obviously inertia is the parameter of the motor. So we have to double click on the motor. Okay, here you can see three options. One is the configuration, second is the parameters, and advanced. Inertia is the parameter. Okay, we have to place it equal to 0.05. Okay, obviously for first reading it is already 0.05. Okay, so no problem. Okay, other quantities don't change. Okay, just whatever the quantities they ask to change, only change those values. Okay, so all the parameters are set. We can run it. Okay, click on play button or run button. Wait for a while. It is compiling. Okay, now it is running. Okay, now we will check. We can change three quantities here. One is the voltage, second is the armature current, third is the speed. So what the reading we have to take? Okay, in second column we have to write down what is the acceleration time. Okay, means what, how much time it takes to run to 120 radian per second. Okay, this is the third is the speed axis. Sorry, I have to select the x-axis zoom. So you have to check what is the acceleration time. Okay, means what, the first point when the speed goes to 120 radian per second. Obviously this is the point. Your first point is this. Okay, this is the cross section. Here the speed is crossed to 120, this location. Take the precise readings. This point. Okay, I think it is equal to 0.1964. 0.1964. 0.1964. Okay, this is the first reading. Okay, I will show one more reading. Other readings you have to take. Sorry, I forgot to change the acceleration. Change acceleration to 0.1. So we will check what is the effect of increasing in acceleration. We are double it from 0.05 to 0.1. Okay, you can check here. As the acceleration increases, the acceleration, sorry, as the inertia increases, the acceleration time will increase. One minute, where is that point? Here. Okay, this it crosses to 120 radian per second at time 0.3917. 0.3917. So you can observe here, as the inertia increases, the acceleration time increases. Okay. Similarly, take the reading up to zero point 0.4 of the difference 0.05. I think you have to take total 8 readings. 1 minute. Sir, there are recordings for at least. Okay, second reading we have to take. What is the effect of armature current limit on acceleration of the drive? Okay, so in this case, okay, hysteresis band we have to put equal to 2 ampere, load torque equal to 5 Newton meter, inertia has to be equal to 0.2. Okay, so we have to change the inertia. Inertia equal to 0.2. And speed reference equal to 120. Okay, it is already 120 radian per second. So current limit we have to change it from 20 to 40 of the difference to, or we can take 20, 24, 28. I am taking it at the difference of 4, 32, 36 and 40. Okay, so first I will put the current limit equal to 20. Okay, one more reading we will take, which is by default present there. After 28 we will take the reading of 30, then 32, then 36 and then 40. Okay, so 30 is by default there. Here current limit is 30, so I will run it now. Okay, when the inertia is set equal to 0.2 and speed current limit put equal to 30 ampere, in that case the acceleration time is equal to it is around 0.7822. For 30 it is 0.7822. Now I will take reading for 20. So the difference in acceleration time will be readily observed. Okay, for 20, okay, when I reduce the current limit, okay, the acceleration time will be more. Okay, it is around 1.3042. 1.3042. Okay, means what? It is increased as the current limit is decreased. I will take one reading for 40 ampere. Now I will increase the current limit to 40 ampere. Again, I will run the experiment. Okay, you can observe the acceleration time is decreased. Take the readings up to 4 decimal points. Okay, the speed, okay, the acceleration time is around 0.5592. 0.5592. Okay, means what? As we decrease the current limit, the acceleration time will increase. Again, as we increase the current limit, the acceleration time will decrease. Okay, third type of readings we have to take to check the relationship between load torque and steady motor armature current. Okay, here we have to set the parameters. Current limit equal to 30 ampere, speed reference equal to 120 radian per second, hysteresis band equal to 2 ampere, and inertia of the motor equal to 0.05 kilogram meter square. Okay, just this point, this parameter we have to change 0.05. Okay, we will take the reading as first reading as 1, second is 2, third is 3, next is 4, then 5, 6, up to 7. Okay. Already the torque is 5. Okay, I will take the reading for this 5 Newton meter. And we have to check the steady motor armature current. In this case, we have to check the value of motor armature current, not the acceleration time. Okay, so here this part, okay, this whole part is the transient. We have take steady motor armature current. Steady means what? When the machine is in steady state, okay, means what? After zero point 0.5, we can see here, you can observe here in the speed graph, after 0.5 second the machine is settled to a 120 radian per second. So after zero point 0.5 you can take the value of the current. So here after zero point 0.5 wherever you can take. Okay, you can observe the average value of this current equal to 6 ampere. Okay, so the first reading for 5 it is 6 ampere, current equal to 6 ampere. Okay, or you can calculate it as what is the maximum value of current, what is the minimum value of current, add them and divide it by 2. Okay, you can take reading like that. Okay, for example, in this case maximum value of current is 7, minimum value is equal to 5, 7 plus 5 equal to 12, divided by 2 equal to 6. Okay, like that you can take the reading. Okay, again under steady state. So second reading I will take load torque equal to 1. Click on this block and I will run the experiment. We will observe what will happen with the value of current. Okay, you can observe here the current has been reduced. Okay, I think the average value is around 2.5 ampere, 2.5 to 3. Okay, I will write it as a, or you can again zoom it out. So I think it is around 2.5. Okay, you can check what is the maximum value of current, what is the minimum value of current, and add both of them and divide it by 2. Okay, so I think it is equal to 2.5 milliampere. Okay, now I will take one reading for 7 Newton meter. I will increase the value of the load to 7. Now I will run the experiment once again. Okay. So you can check here the value of current is increased. Okay, I think it is around 7.5 ampere. 7.5 ampere. Okay, so you can observe here that as the load decreases the armature current decreases, as load increases the armature current increases. Okay, which is according to the theory. So you have to draw 3 graphs. First is the inertia versus time, second is the current limit versus acceleration time, and third is the load torque versus armature current. These 3 graphs you have to draw, and you have to write the answers of these 5 uh, questions. Okay, first question is how the voltage applied to the motor is controlled. Second is the explain working of hysteresis current controller. Third is the why inductance is necessary in series with the armature circuit of motor. Next is the what is the mean by torque ripple? Does this system have a torque ripple? Name the type of chopper used in simulation. How the chopper is controlled. Okay, you have to answer these questions. Okay. First question is how the voltage applied to the motor is controlled. Obviously, we are using armature voltage control method, and by changing the duty ratio, we can change the voltage given to the armature. Second is the working of hysteresis current controller, which I have explained okay before. That is the why inductance is necessary in series with the armature circuit of motor. You can observe here the current has a ripples. Okay, the current has a ripples. Okay, it oscillates. Okay, we have to filter out those ripples. Okay, so that we can get the smooth speed. Okay, so the inductance is necessary to filter out those current ripples. What is mean by torque ripple? Okay, I think this concept we have studied when uh, we are learning about single phase fully controlled rectifier fed DC motor drive, where I have told you what is the frequency of torque ripple when the supply frequency is 50 hertz. Obviously, it is two times the supply frequency, that is 100 hertz. Okay, okay. Torque ripple means what? Variations in unwanted variations in torque. Okay, does this system have torque ripple? Obviously, as the current has the ripples as the torque. Name the type of chopper used in simulation. Okay, we have used a buck chopper, that is step down chopper, and you have to write down how the chopper is controlled. Okay, so how pulses are given to that particular switch, and how that pulses depends on the duty ratio, and how those pulses will govern the value of voltage level given to the armature. Okay, and after that you have to write the conclusion. Okay, here I will stop. Okay, take all the readings. Okay, and draw those graphs. Okay, I will end the meeting now.